Okay, in this video, I'm going to show you the uh, basic and general procedure of using Fluent ICEM to generate mesh for a CFD simulation and how to do the simulation in Fluent. Here I will use this sphere to represent the rocket. Obviously, the real rocket is much more complicated than such a simple geometry. But this tutorial is meant to give you some general idea. So here I simply use a sphere to represent the rocket. Okay. So when we do CFD, what is our purpose? Our purpose is to, use such a numerical tool to obtain useful information, right? For example, for a rocket, right? When it flies at a certain speed, we all know that air is going to, if you attach a reference frame to the rocket itself, then it is air that flows toward the rocket and gives it a drag force, and the drag force is due to the velocity distribution in the airflow. As we know, air is viscous, so the air particle in fact sticks to the rocket surface. For those fluid particles, air particles, very, very close, to the rocket surface, they simply stick to the surface. But away from the surface, the air particles have higher and higher speed. So there is such a velocity distribution in the air around the rocket. And because of such a velocity distribution, so the shear stress arises, and pressure also varies from point to point, which together gives us the drag force. And sometimes we may even have lift force, right? So we want to know such information. We want to know, for example, the velocity distribution in the air and the resultant drag force. So how can we do that? Using a numerical tool like Fluent, in essence, is to solve the governing partial differential equation, the partial differential equation that governs the airflow, which is the Navier-Stokes equation, right? We solve such a partial differential equation numerically, so that from such a solution of the Navier-Stokes equation, we can find out the velocity distribution in the air, and we find out also the pressure distribution in the airflow. Then Fluent is able to combine such information to find out the shear stress, the pressure, force, and then eventually we have, the drag force, all those forces we need, right? Okay, so based on this very simple basic idea of the so-called CFD, computational fluid dynamics, we can see that in order to carry out such a simulation, the very first thing you have to create, in fact, is the very first thing you have to define is the computational domain, because we cannot, we cannot really solve the fluid motion in all the atmosphere surrounding our rocket, right? It's impossible. The atmosphere is, from our perspective, is almost infinite, right? It, takes a huge volume, and it is impossible to solve, the velocity distribution in such a vast space of air. It's both impossible and unnecessary. So we will only focus on the part of space or volume that the most critical and relevant physics takes place. As we know, we have learned this from our fluids class. In fact, for such kind of flow, right, the air flows over a body. In fact, most important physics takes place very close to the body surface. The velocity, in fact, only changes in a very thin layer close to the body surface called boundary layer. And away from this boundary layer, in fact, the fluid flow is pretty much a uniform flow. It just flows with the same speed, same direction. Not very interesting. I'm not saying it's not important, but definitely not as important as the boundary layer, right? Also, some important physics also happens, behind the body. In the rear part of the body. That region is called the so-called wake, W-A-K-E, the wake region. And in the wake region, typically the pressure is low and the velocity gradually recover from the influence of the body. So far away, far downstream of the body, eventually the airflow in the wake region becomes, recovers the original, uniform flow. So, upstream, the air flows toward the body with a uniform velocity distribution, right? But when it passes this body, then in the wake region, you may find that very close to the body, you will have some vortices, and away from the body in the downstream direction in the wake region, you still see the effects of the body, and the velocity of air is not very high. Only far downstream from the body, the velocity gradually recovers to the original uniform flow. So the wake region, this region is also important. So you will want to include this region in your calculation. So you have to first define, a volume, a space in which those important physics takes place, and you want to include such a region in your calculation. And you don't want to calculate, a big region, because it costs computational resources, right? It will take longer to do the simulation. It will take more computer memory to do the simulation, and you don't want that. So this is the first thing you have to do. You have to define a computational domain. That is the space where the important physics, where the airflow really takes place. Those important physics takes place. So although it seems that the only thing that is important is our rocket, but in our simulation, only the rocket alone is not sufficient. Okay, you have to create another boundary, okay, to define a finite computational domain. So I'm going to create a cylinder here, okay, to enclose this rocket. So here this sphere has a radius of 1, which means a diameter is 2. So I'm going to create a cylinder with a radius of about 5. Okay, I'm not saying that this value is the best. Okay, it's the optimal value. No. Again, this is only a tutorial showing you the basic idea. So you will have to, play with such numbers in your real simulations, and you have to do such a computational domain size study, which means you use a certain value here, radius value here, to create a certain size of computational domain and run the simulation, and then you change this size, okay, to for example, to enlarge the domain and rerun the simulation, see what happens. Okay, if the results do not change much, then probably that means your original computational domain size in fact is fine, right? But if you find significant changes in your results, then most likely you will want to further enlarge your computational domain and rerun your simulation until the results stop changing. Okay, to define this cylinder, in fact, I also have to use 2 points along the axis of the cylinder, which I don't have these two points, right? So I'm going to first create these 2 points. So I use this create points icon here and use this tool, okay, explicit coordinates. So I directly specify the coordinates of 2 points along the axis. Okay, here the origin of the sphere, the center of the sphere is at the origin of my coordinate system, 0, 0, 0. So I probably use x equals 0, y equals 10. That's probably too much. 5. Again, I don't say 5 is the optimal value, okay? 0, so I create 1 point here. Well, a little bit too close, but anyways, I will do it anyways. And another point is maybe negative 15. Well, 15 is only this much. Okay, then probably negative 25. Yep. I delete this one. Okay, then I go back to this create modify surface icon and using standard shapes and cylinder. Okay. Radius 5, is that good enough? Probably. Okay. Then to axis points, then I select this point, then press the middle button to confirm my selection. Okay. You can see now I created such a cylindrical surface, right? Indeed, this cylindrical surface encloses my spherical rocket, well, like a UFO, yeah. So I will solve the fluid motion only in the computational domain defined by the space bounded by this sphere and the cylinder. Okay, so I'm only interested in, and I will only solve the fluid flow in the space, you know, in between this sphere and the cylinder. Okay, so this is the first thing you have to do. You have to define such a space. Okay, only you will only solve the Navier-Stokes equation inside this defined space, the so-called computational domain. And the second thing you have to give Fluent is a mesh. Okay, so remember this. Whenever or wherever you want to solve partial differential equations and to get useful information, okay, like velocity, pressure, you have to provide a mesh there. Okay, so basically you will need a mesh everywhere in your computational domain. That's the second thing you have to provide. And third thing you have to provide is the so-called boundary conditions. Okay, one feature of partial differential equations and ordinary differential equations is that their solutions are not unique. Okay, the solution to any differential equation is always subject to a certain arbitrary constant, which means if you add a constant to your solution, usually it is still a solution to the original differential equation. So in order to have a unique solution to your partial differential equations, you will have to provide the boundary conditions, which means I'm not going to solve the data, the physical data at those boundaries of my computational domain. Instead, I will directly give such information at such boundaries. Okay, usually this is totally possible. Okay, you just specify, for example, velocity at the boundaries of this computational domain, right? Then you will have a unique solution. So here I'm going to first make sure that I can apply boundary conditions to those boundaries. I will do that. I mean, I will apply those boundary conditions to those boundaries in Fluent. Right now I'm using ICEM, right, the meshing tool. So here I will do some preparation work to facilitate the application of boundary conditions in Fluent, which is I will first define those different boundaries, right? Because sometimes I will apply different conditions at different boundaries of this domain. So if you do not distinguish those different boundaries, then how can you apply different conditions at those different boundaries, right? Because right now they are just, one whole piece of boundary. So here I will want to define those different boundaries, which what I mean is I want to give different names to those different boundaries. Okay, this is done by creating more parts. So right-click parts, create part. So you can define some new names, okay, for those different boundaries. Say this boundary, okay, this surface, I will call it inlet. Okay, this is probably not the best name, but it certainly is not a very bad name. Hopefully, okay, I click that. Okay, you can see its color changed. Then I press the middle button to confirm my selection. Okay, you can see this new part called inlet was created. To make sure that you choose the correct surface, you can turn off the display of this newly defined part. Okay, you can see this surface is gone, right? But of course it's not really deleted. Okay, it's just become invisible. You can turn it back on. It's still there. Second part, outlet. Well, it's this surface, right? Okay, you can see it's pretty difficult to select that bottom surface because it is behind the side surface, or I mean, it's not really visible. So what you can do is you can press the F9 key on your keyboard, F9. Okay, one of those keys on the very top of your keyboard. F9, then you switch to the so-called dynamics mode. In this mode, you are free to rotate, to move your geometry so that you can see those hidden surfaces. Then you will want to hit this F9 key again to go back to the selection mode. Okay, then you can select this. Then press the mid button. Okay, so the second part or boundary is defined, right? Then I will define say the domain side surface, right? Which is this surface, right? Okay, good. Now I have the outlet, which is this guy, the inlet, and the side of the domain, but we have another very important boundary, right, which is the surface of the rocket. So rocket surface. Here, for simplicity, I represent the whole outer surface of the rocket as one single boundary, one single part. But in your simulation, sometimes you may want to, define a few more parts for the rocket outer surface. Okay, for example, you guys are doing simulations of the flow. You are studying the air brake, correct? So you may want to define the surface of the air brake as a separate part from the rest of the rocket surface, because probably you want to know how much, for example, how much drag is acting upon that brake alone. Okay, the total drag on everything, okay, on the whole surface of the rocket, say, is 2 Newton, suppose. Okay, but how much drag is caused by that air brake alone? This is probably of much interest, right, to you. So in that situation, you may want to define the air brake surface as one separate part. In this way, Fluent will be able to do calculations on that part unknown to tell you how much drag force is on the brake. Okay, now I have all my parts. Okay, then I will go back to create my mesh. In the real world, the rocket is of a very complicated geometry, right? So it it's sometimes difficult to create a very structured mesh around such a complex geometry. So usually we will only pursue an unstructured mesh around the rocket. But one problem of such unstructured mesh is that their quality typically is not as good as the structured mesh. So here we probably want to leverage the advantages of both structured and unstructured mesh. Okay, structured mesh is of high quality, but it's more difficult to create. The unstructured mesh is very easy to create, but its quality is not very high. So here I will pursue a hybrid mesh. However, to do that, I have to pay an extra cost, which is I will have to create an additional cylinder here to enclose my rocket. Yeah, which is probably not the most pleasant thing to do, but I will do it anyways. So I will first create two more points. One point is at 0, -15, 0. So it is here. Okay, and I believe this point is at 0, 5, 0. So I'm going to create 0, 3, 0. Okay. Then I will create a cylindrical surface. Now the radius, okay, this is 1, so let me simply use 2. Then I select these two new points. Okay, a new surface is created, and I will create a new part for this new surface. I will call this part, how do I call it? Inner. Okay, whatever. Okay, this guy. Okay, right now I believe I selected everything here, but maybe not. Okay, I will select also this one and also the bottom side. Okay, so this is my inlet. So this surface in fact is kind of an imaginary surface. Okay, it's only here to separate the computational domain so that I will have very complex unstructured mesh in this region, okay, enclosed by this new cylinder, and I will have a very nice structured mesh outside this small cylinder. So I'm not going to apply any real boundary condition to this surface of the smaller cylinder because it's not really a physical boundary. Okay, I do not know any physical condition along this boundary. It's only a means to separate my computational domain. So there is no need to define those surfaces of the smaller cylinder with many different names. Okay, it's just one whole piece. Okay, to create unstructured mesh in this smaller boundary, I will have to define so-called body. Okay, at this point you can you can understand this body as you know, uh, a volume in which you want to have unstructured mesh. Okay, so if you do not want an unstructured mesh in a certain space, you don't want to create a body in such a space. But if you want unstructured mesh in a certain subspace, sub-volume, you have to create a body, or more precisely, a body point in that volume. And you have to give a name to that body or that volume. So here we are call it zone unstructured mesh. Okay, unstructured. I will use a centroid of 2 points to define this body or body point. Okay, which 2 points? Okay, very easy. I will simply choose this point and this point. Okay, then at the very middle of these 2 points, you can see this so-called material point or body point was created. Okay, you should make sure that this point is totally, entirely inside the volume in which you want to create the unstructured mesh. Okay. What ICEM will do is it will put one mesh cell at this point, then it will put the second mesh cell next to the first cell, and so on. Okay, so basically it will put one more cells starting from this point. Okay, so the mesh cells gradually grows. Okay, it grows from this point to the outward. Okay, so the mesh cells keep growing until they touch a surface. Okay, so it keeps growing, one or more mesh cells, then it touches the surface of the rocket, right? Then it stops. Okay, so on and so forth. So eventually, such unstructured mesh will fill the whole space bounded by the rocket surface and this cylinder surface. Okay, to create such an unstructured mesh, what you need to do is to go to this mesh tab, use this global mesh setup, then set up a mesh size, the size of the sphere. As I said, radius is 1, so probably use 0.1. Display. Okay, you can see how small it is. Okay, this big. Okay, this is the maximum size of the mesh. Then you go here, compute mesh, then push compute. Wow, 600,000, 1 million, obviously 2 million, 3 million. Obviously 0.1 probably is a little bit too small size, but I really suggest that you do not push this interrupt button, because my experience is that whenever you push it, this code crash. Okay, it crashes. So it's better to wait and wait and wait until you lost all your patience. Obviously 0.1 is really too small. Now I have 20 million tetrahedra cells, and I am still less than 50% done, which is terrible. Okay, we'll push this button anyways. Okay, let's see what happens. Nothing. nothing happens. But I know that it's not happy with that. Okay. Okay, it is trying to figure out what I'm trying to do. What I'm trying to do is to pause you. Okay. So stop. Stop. Okay. Did you stop? No. Okay. Obviously it is still working. Yep. Then it is going to crash. See? Okay. That's why you should not do that. Oh, very good. It didn't crash. Good. Okay, let me save my project. Okay, great. No damage was done. So change my. So that's really no reason to use such a small thing. Okay, 0.1. Let's use 1. Oh, so big. Okay. And let's do it again. Mesh already exists. What do you want to do? Replace it with my new mesh. Okay. You say, I don't see any mesh. Really? Now you see it, right? It's a very coarse mesh. Definitely not good enough, right? So you really want to do something. First, of course, you can change this global mesh size. I mean maximum size. 0.1 is too small. I know that. How about 0.4? That's probably better. Do you think? Okay. 0.4. Kind of dangerous, right? Okay, apply. And let's do it again. Yeah. Okay. That's not too bad. Okay. Great. Yeah, that's not too bad, right? Okay. That's not too bad, but still not good enough. Why? Because as I said, the most important physics happens in what? In the boundary layer, right? Around the rocket surface, and the boundary layer is very thin. Definitely much thinner than the size of such a big, tetrahedron. So if you only use such big cells, it's not going to catch the physics taking place in those very thin boundary layers. Okay, so what you should want to do is this. Okay, you will change the mesh setup, the mesh density at the surface of the rocket. So I'm going to turn off the display of this inner surface so I can select this rocket surface more easily. Okay, I say that it's 2 hemispheres. Okay. Now for the mesh cell close to this surface, okay, I'm going to use the maximum size of not 0.1. I won't use 0.01, maybe even smaller. No, that's too small. 0.1 and height ratio is 0.02. Okay, this ratio is used to control how fast or how slowly the fine mesh is transitioned to more coarse mesh. Okay, so the smaller this number, this number has to be greater than 1. Okay, otherwise there's no any transition. If it is 1, then the mesh size is pretty much always the same size. It has to be greater than 1. So the finer mesh gradually grows in size. Okay, so the closer this number is to 1, the more smooth the transition is. I think I also need a few layers of prisms, so I will say 6 layers. I don't know what it is. Okay, at least I can. Okay, I will not do this right now. And okay, recompute, replace. Okay, now you can see over this surface the mesh becomes really fine, but probably still not fine enough. Okay, no, not this one. This is the interface. Much finer than the rest of this inner cylinder, but probably, as I said, is still not fine enough. So I will want to, you know what, yeah, here you can see for different parts, right, you also can define, the maximum size, height ratio here, those things. So here I want to create a few layers of cells around the rocket surface. Okay, those layers are called prisms. How to tell you? Whoa, okay. You can think of them as like those tail shape of cells. You pave one layer of tails around this surface, then you add a second layer around this surface, and so on. Okay, so so here I'm going to add maybe 6 layers, and I don't know. I don't know if it is set up here. Size ratio, medium size, maximum height limit factor. I have no idea what this is, but I dare to try that. Probably let me try 0.05, see what happens. Okay. Apply. Okay, that's correct. 0.05. Did I have the point? No. So probably this is not the correct place to do that. Size ratio. Okay, I frankly I do not know. There should be a place to set up these layers. Okay, let me try that. Okay. Okay, I do not really see any prisms around my rocket, but probably that's because I didn't turn on those volume cells. But seriously, I still do not see any prisms. Okay, this is an issue. Okay, I do not know how to solve it. There must be some way to do that. Prism height limit factor. Okay, you probably want to Google the internet, ask ChatGPT how to do that. Anyways, yeah. So let's move on. At least we now have such a unstructured mesh inside this region. What you really want to do is you want an even finer mesh around this surface. Okay. Although I'm not 100% sure how to add such prisms around in the unstructured mesh region, but I think, of course, you can Google it, you can ask ChatGPT about it. But for me, if I want to find a way to get around of it, I will add an even smaller cylinder around, or maybe even a sphere shape surface to enclose my rocket, and I use a really fine mesh inside that small region. Okay, that is what I can do. Okay, then you can see I still don't have any mesh in this outer region, right, which is very normal because I didn't define any body point in this outer region, so the unstructured mesh will only grow and stop growing when it touches this inner cylinder surface. I don't want any such unstructured mesh in this outer region, okay, because I want a structure mesh there. So to create a structure mesh, the method is very different from creating such an unstructured mesh. You do not want to define a body, okay? Instead, you have to define a block. Okay, here I will create a block, and again, you have to give it a name, okay? Here I will simply call it initial block. Okay, it's a 3D block. Okay, so 3D apply. Okay, you see the block, right? This is a block. Okay, then I will do some association. Okay, associate. Okay, I will use this associate edge to curve thing. So I will turn on the curve. Okay, I will turn off the surfaces. These four edges of my block will be associated to this curve. Here, by the way, I checked the box before project vertices, so you can see those vertices of my block automatically, slaps onto the geometry, which is pretty nice. So these four will be associated to this guy. Okay, that's pretty much good enough. Okay, if you directly create a mesh in this block, it will create a mesh, in fact, everywhere, okay, including the space inside this smaller cylinder, which we don't need a mesh there because we have already had a mesh there. So in order to not creating mesh in that space, I will cut my blocks, okay, and eventually delete the block corresponding to this inner portion. What I'm going to do is I will create a so-called O-grid. So this icon, okay, split block, and using the second tool, okay, O-grid. I select my block, which is the only block I have. Press the middle button to make sure I select it. Then I will select two surfaces, which is this two ending surfaces. Then I will apply. Okay, now my block is split into 5 blocks. Okay, 1, 2, 3, 4, and this central block. And I will then cut my block, okay, using this one, split block. To cut, okay, press left button and then move up, down. Cut here, press the middle button, then press the left button. Okay, then cut at roughly here, right? You don't need to be very exact because you will do association. And press the middle button. Okay, that's it. I will turn off the mesh so I can see things more clearly. Okay, then I will do a little bit more association here. But before I do that, I will delete one block, which is a block corresponding to this cylinder, right? Smaller cylinder, which I'm going to. Okay, if right now you delete block, okay. If you do that, you may find that it's very difficult to select the central block. Oh, I was successful. Okay, I selected the center block, but typically it's pretty difficult, okay, because there are so many blocks. So in such a case, what you can do is you can right-click blocking, then turn on index control, which allows you to control which blocks you want to display here and which ones you want to hide from being displayed. So if I increase the lower limit of dimension number 3, you can see, oh, right, those outer blocks are all become invisible. Now it's very easy to select this block, right? It's right here. Okay, it is deleted. Okay. Then I can do my association. Say this one, this one, this one, this one will be associated to this guy, and this side. Okay. Then reset all the blacks. Those invisible blocks go back to be visible. Okay, then I have already had my mesh setup, right? The maximum size is 0.4, which is fine. Here, if you want, you can use a different number, okay? Then, to create the structural mesh, you expand this blocking and check the box before pre-mesh. I'm sorry, that's not the correct order. Okay, you have to go to blocking. Yeah, it's apply. Then go to blocking. Then click this pre-mesh parameters. Then click apply. Then it will tell you how many structure cells will be created. Okay, it's a very small number, so it should be fine. Then check the box before pre-mesh. Then check yes. See, now you have a pretty nice, pre-mesh structure mesh being created. Okay, it is only created outside of the inner cylinder region, because you only have blocks in that region. Okay, the block corresponding to this inner cylinder has been deleted. Okay, so wherever there is no block, there is no structure mesh. Wherever there is a block, there is a structure mesh. Okay, now you have both structure mesh and unstructured mesh, which is inside that. So you have a last thing to do. That is, you have to somehow merge these two pieces of mesh. Okay, right now they are kind of two separate mesh. Remember that a pre-mesh is not a mesh. Otherwise, it should be called a mesh, not a pre-mesh. So you have to convert it to a real mesh. So right-click pre-mesh, convert to unstructured mesh. You say, huh? Why it becomes unstructured? It's not really become unstructured. It only takes the file format ICM used to store an unstructured mesh. Okay. Either way, I'll say mesh already exists. That's right. We have already had some unstructured mesh there. What do you want to do? You want to merge. Okay, merge. Okay, now even you turn off the display of pre-mesh, you still see this structure mesh, because now it becomes a real mesh. Okay, it's already been there. It's still not good enough, because this at the interface between these two sets of mesh, okay, you have two different meshes overlapping. Okay, that's not good. So you have to edit your mesh and go here, merge nodes, use this merge meshes. Yeah, okay, makes perfect sense. See, this icon shows you what it does, right? You have structure mesh, unstructured mesh. You want to merge these two meshes. Merge surface parts. This surface is this inner cylinder surface, right? We have already defined it. Okay, you can see I defined it for a purpose, right? So that I can select this surface here, accept, apply. Okay, it's done. See, at the surface, at the interface of did I do it right? Merge volume mesh. I think so. Although the mesh looks pretty weird, I should say. I want to take a look. Okay. Surface solid. I don't want transparent. That's not so correct. Okay, that's not so correct. Something seems wrong here. Okay, let me see this side again. It's not, seems not accurate. Okay, I will double check. What's going on here? Okay. do here? I think I didn't make a mistake, but obviously I made some mistake. Interesting. Okay, I did that. I had to association to that. Which I believe is correct. Okay. Then here we have some surfaces, inner surface, and which is correct. So it's pretty weird that I don't want that. I want to take a look. I want it to be not transparent. Probably you know that. That's weird. That's weird. Okay. Okay. Anyways, this is the basic process, okay, to create such a mesh, hybrid mesh, and also create, those boundary surfaces as well as, different zones, okay, unstructured zone, and okay, here this initial block should be called another name, say zone structured mesh zone. Okay, so I have two zones and many different services. Then afterwards you want to save your project, and I really want to know the mesh quality probably is not very high. Yeah, not very high. There are definitely some problems, but I don't have time to fix those problems now. So eventually you want to output your mesh, select the solver, which by default is Fluent, then click write input. Save current project first. No, because I just saved it. Project number 1, open is a 3D mesh. Okay, give it a name, Fluent is fine, done. Okay, done with translation. Then you will have such a mesh under your own folder, okay, where you save your project. So here you will see such a mesh file called fluent.msh, which you can read it into Fluent. Okay, I will tell you how to fix this problem maybe tomorrow. Well, if I can figure that out tomorrow, by tomorrow. Also how to do the simulation. Okay. This is the end of the tutorial.